So in order to become happy, I invite you to take this wave function and do a little trick with it. Make it psi star times psi and see what happens. You can try doing it in your notebooks, and I will see if I have appropriate slide with it. Start of lecture level. Okay, it was introduction. Okay, so this is what we are going to get. And it's not a big secret, we just will prove it. So after taking the probability, the psi star times psi, we are going to get the Gaussian function again, but without any crazy imaginary numbers. And we would be able to bring it into the shape with initial times a coefficient which shows expansion in time. So the original hypothesis that electron is so aggressive that it wants to take all over the space is probably correct based on this calculation. So it will become fatter and fatter instead. And let's get to this point with a little more details. So the bits will expand. I'm celebrating reasons today. I'm just showing equations, but it's very bad. It's bad both for me and for you. It's much better if I derive it before.
Can you go back a slide quickly?
Yes.
I have a question. Sorry, back one more. All right, I have no idea where we were. I guess I'm confused on what is the n squared?
Normalization.
Oh, it's the normalization?
Yes, yes. Okay. Wave functions need to be normalized, so that integral of wave function square will always be equal 1.
Okay.
And we can always find it, but if you are short in time, we can leave it for the future.
Okay.
Or if you have some reasons to skip it temporarily, just for the sake of time. Okay. So here is the wave function psi, and here's the wave function star. How do they differ?
The left is the complex conjugate.
Hmm?
The left is the conjugate.
Yes, yes. So how do you, if you have a function, or just well, it is already written here, but I write it once again. So e to the power minus x squared divided by sigma divided by something. T divided by m. So what does it mean, complex conjugate? What does it mean, this star symbol? I know that.
Time you see now, you just change the sign.
Right? Did you hear it? I don't know what you're doing in class. So wherever you observe symbol I not like a person, I like a letter, mathematical symbol. You swap the sign. If it was plus, you make it minus. If it was minus, you make it plus. And then it is your wave function star complex conjugate, right? So it is what we have here. It is plus at this place and minus at this place. How do we multiply these two exponentials? We add together their powers, right? And we want to be good cooks. We do not want to eat raw food. We want to cook it so that it will be easy digestible. In math, it means like factorize it in the shortest possible form, like try to simplify it. You can be correct, but hard to digest. So, and here, how do you do it? If you have summation of two fractions, denominator, which denominator? Common what?
Denominator.
Okay, so if we consider this little thing x as a, x squared, and here is another x squared as like a, and this denominators is minus, we can call it b, and denominator is plus, we can call it c, and then you multiply the denominators in the new denominator and you sum them in the new nominator, right? No one objects. And if we do it carefully, I promise I use it in the past. And you can practice it if you like. But what happens? What happens? So if you take this b and c, you multiply it in the denominator and sum them in the numerator. When you sum, then this part with imaginary unit comes once with plus and other times with minus. So they cancel, which makes easy numerator. And in the denominator, what do we see? Another little trick from middle school. X plus y times x minus y equals what?
X squared plus y squared.
X squared. And which sign goes to? Huh? Minus. Minus y squared. Right? This doesn't surprise you. So we replace this product of x and y onto x plus y and x minus y onto x squared plus minus y squared, and we get the plus sign because our y contains imaginary unit. Okay? So let's, is it visible? Is it large enough to see? No. Okay, then I need to re-expand it. Please. So it was x squared times sigma squared over 4 plus da, da, da. And what I just wanted to point you on, that sigma, 1 power of sigma cancels. And then after this manipulation, is this visible? Then we are getting again Gaussian function as decreases as x goes to plus or negative large number. And here we do have the width plus some expansion coefficient and t squared. And this t squared came from algebraic manipulations. We didn't guess it. We obtained it as the result of this processing. So we set up a goal, did some, applied our protocol of predicting the future, performed mathematical manipulations, and got this answer. This is something that we can analyze as scientists. I was not lying, or I was lying acceptable meaning. So this is a Gaussian wave function that has this shape as function of x. And at time 0 it has 1 width, and as time passes by you get it broader and broader, right? So whatever stays in the denominator is the width of the function. And this width, we can write it n square e to the power minus x squared divided by sigma x of t. And the sigma x of t is how broad, how far this electron did expand in the space. So if we draw this sigma x as function of time, it starts from initial value, and what does it do later? Does it decrease or increase?
Increases quadratically.
Increase quadratically. So this is base value. So appetite of this aggressive expansion becomes more and more. So it takes more and more space. Good? No objections. Now, let's have a second glance. On the answer of your homework, which is right here. So, you're not going to derive anything, or almost nothing. But prepare. Right now, there will be an important message worth of translating into your own words and writing down or memorizing. So there I'm very clear in mind and just try to find best words. We got acquainted with two types of space. We got regular position space, x, and we got momentum space, p, or we can call it k. And your homework assignment was to get expansion coefficients for predicting future, but on the other hand, it was recasting your wave function in the momentum space. So we converted from the space of position in true space into range in the momentum space. We saw that wave function with this momentum we have larger expansion coefficient, with another momentum lower expansion coefficients, and then we have distribution of this plane waves with different values of momentum. This representation, this expansion coefficients, is a replacement of wave function in a position space, and it is the same object, the same function, but it can be represented in different spaces, in our regular, intuitive, simple position space, and at the same time at the momentum space. So the answer from your homework is wave function in momentum space. Wave function in momentum space. This was statement number one. Now, if you know for sure that our electron has only one value of momentum, that it is like a plane wave moving with given velocity one side, then momentum is certain. Right? Or if you know for sure that our electron is classical path approximation is pointed at a very, very narrow vicinity, then we can call that the position is certain. But if it has width, then it means it is uncertain. The amount, the width, the value of this variable sigma is uncertainty, is plus minus how much it deviates from central point. I don't know how to say it. Width, v d t h equals uncertainty. Width is uncertainty. It was statement number 2. Now, statement number 3. Let's look on our answers and analyze what is uncertainty in position, what is uncertainty in momentum. In position, we discussed it. In momentum, we can recast this equation that you get in your homework in this form, where you get p squared over sigma sub p. Where this sigma sub p will be to a sigma x. We just redefine it. But what is really interesting, the distribution in momentum doesn't change in time, at least for this problem. So the width uncertainty of momentum remains constant. Uncertainty of position changes, uncertainty of momentum doesn't change. If you need to go to other class, please go forward. It is recorded and you'll see it. Now, a little math. It is exactly 11:50 right now. Now, let's try to multiply these two things: uncertainty of position and uncertainty of momentum, which we already know in exact answers in radical. So here is our uncertainty of position that grows and uncertainty of momentum that doesn't grow. So we just take these two functions and multiply. So if we do it very carefully, we see that many things can be cancelled. And what is important is here we have sigma 0 in numerator, here in denominator, and they cancel. Cancel here, cancel 0. There. So, and at time 0, second term doesn't apply, right? So it will grow later, but initially we can tell that it is 0. What do we get? H bar square with some factor. H bar square. Here I'm getting divided by 2, but the factor doesn't mean is not so important. It is important that product of uncertainty of position and momentum uncertainty of position and momentum are not independent. They are connected in the following way. Their product gives specific mathematical relation. So it is equals h bar square plus some coefficient alpha times t squared. Right? Which means that sigma x times sigma p, so it can be equal to h bar square over 2 at time 0, but later on it will be always bigger. Right? So it never gets smaller. It can stay the same or expand. So our original hypothesis that electron is so aggressive that it wants to play civilization and expand on new continents, this property of electron to take more space, results in philosophically important principle of quantum theory, which is known as uncertainty principle. So because we found that it wants to expand just because of our ways to predict future, but later on, logically, because we found its tendency to expansion, we recast it in the form that position and momentum cannot be measured simultaneously with arbitrary precision. Or, in more mathematically, the product of uncertainty of position and momentum has some minimum value, and then it always grows. Right? So, sigma x sigma p grows with time. So it has some minimum. This h bar square thing is a minimal value of uncertainty. position and momentum can be known precisely. They have uncertainty. Okay? I hope that when I click the button, it will be my favorite slide. Yes. Okay, thanks much for staying. I have good intentions to return those minutes that I borrow and accumulate from lecture to lecture. Meaning that one time you either cancel the lecture or go away like half an hour earlier. So I'm trying to count and accumulate. Thanks for staying. And see you on Wednesday. See you and your homeworks.